All right, have you ever looked up and just wondered, what's really up there? I mean, way up there? Well, today we're going to take a trip. We're starting right here on the ground and going all the way to the very edge of space. We're going to explore this invisible shield that protects every single one of us, layer by layer, to really get what makes our planet work. Let's dive in. Just look at that. When you see Earth from space, this is what you see. This incredibly thin, fragile blue line. That little glowing halo is everything. It's the air we breathe, it's our planet's thermostat, it's our shield against the harshness of space. So, what is it exactly, and how in the world does it work? Well, that's what we're here to find out. Okay, so before we start climbing, we gotta know what we're actually traveling through. Let's do a quick pop quiz. If you had to guess, what's the number one most common gas in the air all around us? Most people will probably say oxygen, right? Makes sense. But the numbers might just surprise you. Yep, surprise, it's nitrogen. A whopping 78% of the air you're breathing right now is nitrogen. You heard that right. Now, we can't just breathe it in and use it directly, but it's absolutely essential for life. It's a key building block in the food we eat. So in the atmosphere, it's kind of this stable filler gas. But without it, our planet just wouldn't work. Okay, and now we get to the one we all think of. Oxygen. It comes in at about 21%. And, this is the good stuff. This is what keeps us and pretty much most other life on Earth going. So think about that for a second. Between just nitrogen and oxygen, we're already at 99% of the air. So this chart really puts it all into perspective, doesn't it? You've got your nitrogen, you've got your oxygen, and then look, everything else, argon, carbon dioxide, all those trace gases we hear so much about, they're all squeezed into that tiny little 1% sliver. It's absolutely wild to think that so much of what regulates our planet's climate is happening inside that tiny fraction. All right, so now we know what our ocean of air is made of. It's time to start the journey, so buckle up. We're starting right here at ground level, in the layer we all know and love. Okay, this graph right here, this is going to be our map for the whole trip. It's pretty simple. Going up is altitude, and across the bottom is temperature. And you can see our first stop right there at the bottom, the troposphere. It goes from the surface all the way up to about 12 kilometers. And notice that line? As we go up, the temperature goes down, colder and colder. So the troposphere, this is where we live. It's where all the action is. It's the thickest, densest layer holding most of the air and pretty much all of the water vapor. And that's why this is where all our weather happens. But here's the really important part, the key to understanding this layer. It's heated from the bottom up. The sun doesn't heat the air directly. It heats the ground, and the ground warms the air above it. That's exactly why it gets colder when you climb a mountain. Now hang on to that thought, because it's going to be super important later. Okay, we've hit the ceiling of our layer, a boundary they call the tropopause. It's time to punch through it and keep on climbing. Things are about to get, well, a lot weirder. Let's check back with our map. Okay, we're now officially in the stratosphere. This layer goes all the way up to about 50 kilometers. But hang on a second. Look at that temperature line. It's doing something totally bizarre. It's reversed. Instead of getting colder, it's actually getting warmer the higher we go. What on earth is going on? Well, the answer to that little puzzle has a name. Ozone. You've heard of it, right? The stratosphere is home to the famous ozone layer. And its job, well, you can think of it as our planet's built-in, heavy-duty sunscreen. It's up there just grabbing onto the sun's most harmful ultraviolet radiation, stopping it dead in its tracks. And that absorption is the whole secret. When the ozone layer soaks up all that UV energy, it basically turns it into heat. So the top of the stratosphere gets warmer than the bottom. And boom, that's the reason for that weird temperature flip we just saw. It's a perfect example of our atmosphere literally working to protect us. Okay, let's keep going. We're pushing past the stratopause and heading into our next layer, the mesosphere. This takes us up to about 85 kilometers. And just look at our map. The temperature is taking an absolute nosedive again. I mean, it is seriously plummeting. Yeah, we are now in a land of extremes. The very top of the mesosphere is literally the coldest natural place on Earth. We're talking like minus 90 degrees Celsius. Brr! But it also does something really cool. It protects us. You know when you see a shooting star? That's not a star at all. It's a meteor, a piece of space rock, burning up because of the intense friction right here, in this layer. It's our cosmic shooting gallery. All right, time for one last huge jump up. We're entering the thermosphere, and this layer is massive, extending for hundreds of kilometers. Now, Look at that temperature graph. Just wow, it's going completely vertical. The temperature here absolutely skyrockets to unbelievable levels. So why the crazy heat? Well, the air up here is super, super thin. But what little air there is gets blasted by the sun's most powerful unfiltered radiation. This makes the individual particles incredibly energetic, which is what we measure as high temperature. This is also the layer where the beautiful auroras happen, the northern and southern lights. It's where the International Space Station hangs out too. Now you're probably thinking, wait, how does the ISS not just melt? And it's a great question. It's because even though the temperature is high, there's almost no heat. The air is so thin there's just aren't enough particles to actually transfer that energy. It's a cool little physics puzzle, right? And finally, we've made it. The exosphere. This is the last stop, the outermost edge. There's not really a hard line here. The atmosphere just gets thinner and thinner until it just fades away into the vacuum of space. This is where tiny particles can literally just float away from Earth's gravity and never come back. Our trip to the top is complete. Okay, so let's just pause and think about the journey we just took. We went up and it got cold, then it got hot, then it got crazy cold again, and then super hot again. What is with that pattern? What's the secret code that defines these layers? When you look at the whole trip on one chart, you see it plain as day. That zigzag, that temperature roller coaster. It's not random at all. That shape is the structure of our atmosphere. Every time that line makes a sharp turn, that's a boundary. That's where we enter a new zone with a whole new set of rules. So this is the big question, right? Why this specific roller coaster ride? What's actually causing these massive, predictable swings in temperature that make our world what it is? And here it is, the big reveal. The secret is something scientists call temperature gradients. But all that really means is that the layers exist because of the temperature changes. The boundaries are simply the points where the source of heat changes. First, it's the warm ground. Then, it's the ozone layer absorbing UV light. And finally, it's the raw energy of the sun at the very top. That zigzag isn't just a graph, it's the blueprint of our atmosphere. Okay, so now that we've seen all the individual parts, let's zoom all the way out. Because the most important thing to get is that the atmosphere isn't just floating there by itself. It's not in a vacuum. It's just one piece of a giant, interconnected planetary machine. See, our atmosphere is in a constant, complicated dance with everything else. The oceans, the continents, every living thing. All these systems are woven together, interacting, creating this incredibly delicate balance. You can think of the atmosphere as the conductor of a huge orchestra, making sure everything works in harmony to keep our planet stable and, well, livable. And that really brings us to the final, crucial thought. We live inside this amazing, complex system that has kept itself in balance for a very, very long time. So the question we have to ask ourselves is, what happens if we start pulling on those threads? What happens if we disrupt the balance of this thin blue line?